Thank you for joining us for this informative American Institute of Chemical Engineers webinar sponsored by Provenance Consulting, the importance of understanding process when implementing your mechanical integrity program. Our speaker is Vipin Vijayakumaran. Mr. Vijayakumaran complements his advanced education with practical industry experience to provide value to his clients as a mechanical integrity consultant for Provenance Consulting. His master's degree in mechanical engineering has been supplemented with professional certifications from the American Petroleum Institute as a certified pressure vessel inspector and certified piping inspector. Vipin has 6 years of professional experience in oil refineries and petrochemical plants in project engineering, design engineering, mechanical integrity, and inspection. One quick note before I turn the session over to Vipin. As described more fully on this slide, the American Institute of Chemical Engineers assumes no legal liability or responsibility for the use or misuse of the content in this webinar. And now I'd like to welcome Vipin Vijayakumaran. Hello, Vipin.
Hello, Pamela, and thank you for the introduction. So firstly, I'd like to thank the American Society of Chemical Engineers and Provenance Consulting for giving me this opportunity to present this webinar and kind of share my experience over the years that I've gained. So the intended audience for this webinar, when I was first typing it up, would be reliability engineers and process engineers and other inspection professionals who are kind of involved with implementing fixed equipment mechanical integrity programs at different facilities. So I'll start off the webinar by going over a quick overview. So firstly, I'd like to describe what is fixed equipment mechanical integrity, and I'll go over it by referring to it as FEMI throughout the process. Then we'll look at some process conditions that can affect your fixed equipment, and then we'll look at a couple of case studies where process changes have caused fixed equipment failures, and then we'll discuss some actions that you can take to ensure that your process conditions do not cause failures and upsets at your facility, and eventually how you can incorporate these considerations, these process considerations in your FEMI program, and overall how you can improve your FEMI program with a better understanding of process conditions. Now, what is fixed equipment mechanical integrity, or FEMI? Going over fixed equipment. The fixed equipment, what I want to include, and what includes the fixed equipment, is your piping, your pressure vessels, including your reactors, scrubbers, and other pressure equipment, your heat exchangers, storage tanks, your boilers, and your relief devices, including your rupture discs and your safety relief devices. By mechanical integrity, we mean the overall management of critical processes to ensure that it is designed and installed correctly and it operates throughout the life cycle of the equipment, to ensure that it's fit for service throughout the life cycle of the equipment. And by equipment life cycle, I mean right from design, installation, and whenever you're commissioning the equipment into construction and commissioning into operation, whenever you're installing it at the facility, whenever you do some repairs or modifications or replacement in kind, whenever you do it to that equipment, ultimately all the way until retirement, all the way till you take the equipment out of service when it is no longer suitable. Now, what are some of the elements of the FEMI program? The first thing is documentation or process safety information. So your process safety information includes your design drawings, your manufacturer data reports, including your U1As and U4 forms, your piping line specification sheets that you constructed the piping according to that line classification, and also your manufacturer data plates that you get from the field. The next element is corrosion control documents. Corrosion control documents basically provide you with guidelines to identify damage mechanisms, susceptibilities of pressure-containing equipment and their related corrosion causing components, and some recommended actions that you can take to mitigate failures that are caused by these damage mechanisms. The next element is inspection plans. Inspection plans are specific for each and every piece of equipment that you have at your facility, and they are built up according to industry standards and equipment-specific considerations that you might have. The next element is your management of change process, which is a review and authorization process for evaluating proposed changes to your facility so that you don't have any unforeseen hazards that are introduced into your process facility that damages the facility or the employees that are working at your facility. The next element is integrity operating windows. Integrity operating windows are basically established limits for process variables that can affect the integrity of your equipment when it operates or when it operates in a way that it deviates from the established limits for a length of time. The next thing is your fitness for service. Your fitness for service is a comprehensive industry standard practice that is used to analyze and evaluate and monitor equipment that have flaws and have sustained damage or they have aged over time and they cannot be evaluated to the original construction code. So this is like this is an industry practice that you have to ensure that your equipment is fit for service by doing some advanced analysis techniques. Now, process conditions can be at a very high level be characterized into two separate categories. The first category is chemical parameters. Chemical parameters, some examples of chemical parameters are your pH levels, your water content, your sulfur content, your ammonia limits, your total acid number, your acid strength, your inhibitor concentration, your chloride contamination levels, your oxygen and carbon dioxide content. There are many more, but just for the time limit of the webinar, I'm just going to limit these to these conditions. The next bucket of conditions that you have are physical parameters. Your physical parameters are basically your pressure, temperature, dew points, your drying points, your heating and cooling rates, your flow velocities, injection rates, and vibration limits. Now, for this webinar, what I'll do is I'll cover two physical parameters, that is your pressure and your temperature, and we'll cover two subcategories of them: overpressure and exposure to vacuum for the pressure scenario, and operation of equipment in the corrosion under insulation range, and equipment that are operating below the minimum design metal temperature in the temperature category, and I'll go over two chemical characteristics, chemical parameters, that is your high chloride levels and your low pH conditions, and how they can damage your equipment. Now let's talk about an overpressure scenario. Overpressure can be caused by loss of cooling, unexpected addition of heat, change in the quantity and rate of addition of your catalysts and reactants. It can also be caused by operator error and deficient operating procedures that you might have. As a consequence, what can happen is it increases the possibility of your leaks from flanges, from packings, from seals, and from other instrument connections that you might have on your process equipment. What it can also cause is plastic deformation on your piping and pressure vessels. By plastic deformation, I mean those components or that pressure equipment that is subjected to an amount of stress, and it has deformation in such a way that it's not reversible. So it's like a permanent deformation that you might have on your pressure vessels and your piping. So in those cases, it affects the pressure retaining capacity. So you might not be able to operate it at that pressure or that temperature or whatever your facility is operating at if you have plastic deformation. And as the more severe scenario would be that you have catastrophic rupture of the system resulting in release of materials that can cause a local fire or a small vapor cloud. Now, to better understand how overpressure can cause catastrophic failure at a facility, we'll look at a case study. So this case study, what I'll go over is what happened at U.S. chemical plant in 2006. So the plant produces paint additives for different chemical processes. So what happened was they produced these paint additives by polymerizing acrylic monomers in a 1,500-gallon reactor. So as a precursor to the incident happening, the plant management received a large order to produce these paint additives. Now, now to scale up the production, what they did was they added additional recipe to the additional monomers to the recipe, and what they did was they added all the monomer that was needed to the initial charge of the reactor. So as a result of this, what happened was it doubled the rate of energy release in the reactor, which exceeded the cooling capacity that it was designed for. Now, as a result of this, what happened was it caused a runaway reaction, and in the end, it resulted in catastrophic failure of the equipment, leading to a vapor cloud explosion and multiple fatalities. So as you can see on the image on the bottom right corner, it is pretty graphic that you can see that that plant had to be completely rebuilt, and I got this case scenario from like a Chemical Safety Board investigation report, which had a lot of details how this failure happened. Now the next scenario is exposure to vacuum. Exposure to vacuum can happen whenever there is failure of a heating medium to provide the vessels or tanks, which could cause low temperatures and lead to condensation of vapors, which results in a vacuum scenario. Another scenario where you can see vacuum is liquid-filled vessels. When they're being pumped out, you can see a vacuum scenario if your tank does not have adequate vacuum protection already designed in. Another scenario that we see vacuum failure is any vessel that is exposed to ambient conditions and there is a sudden drop in the ambient temperature, which causes the vapors in the vapor space of the tank to condense. What happens is, as a catastrophic collapse of the tank happens towards the inside. And the image is actually a pretty good example of where the tank did not have adequate vacuum protection and a pump out scenario was happening at this tank. The next condition is temperature. Temperature specifically operating in the corrosion under insulation or CUI range. So CUI is a very common and very difficult to detect damage mechanism that you find commonly in most oil and gas facilities. CUI can be very expensive to mitigate and very, very difficult to detect because most of it is under the insulation, and you might have to do some detailed techniques which I will describe later to detect CUI. Mostly you can just detect, if you don't have a program in place, it's probably when you have leaks or when you have failures is the only time that you can detect that you have CUI. Now, some of the causes for CUI are in insulated piping and equipment that are operating in temperature ranges between 10 and 350 degrees Fahrenheit for carbon and low alloy steels, and between 140 and 400 degrees Fahrenheit for stainless steels and duplex stainless steels. It can also happen in equipment that have like cyclic thermal operation or are in intermittent service. Now, as a consequence of this, like I described earlier, it can cause the leaks leading to loss of containment. It can also cause metal loss on your equipment and piping. So you might have to re-rate your equipment, or derate your equipment if you have metal loss, which reduces your pressure retaining capacity of the equipment. And lastly, the most expensive consequence of CUI is going to be repairing all your equipment and replacing it. Because when you're repairing equipment, you might have to bring the equipment out of service, and you might have some process upsets, and you wouldn't be able to have any economic benefits while going on. Same way about replacement. Now, the next temperature scenario is equipment that is operating below your minimum design metal temperature. Some of the causes for the equipment to operate below that temperature is when the process fluid refrigerates and it goes below the designed MDMT of the vessels. This might be natural gas or anhydrous ammonia that are examples of process fluids that can auto-refrigerate. It can also happen if the ambient temperature of the equipment, ambient temperature nearby of the equipment is below the MDMT of the equipment. Or when a process fluid is withdrawn at such a large rate that the cooling exceeds the heat available from the ambient sources. And also it can happen when you have a loss of a heating medium within your tank or your pressure vessel. And as a consequence of the equipment operating below the MDMT, what can happen is brittle fracture of the equipment can happen. Brittle fracture is always sudden and it occurs without any apparent plastic deformation of piping or equipment. Now, to better understand this, I'll go over a case study and I'll go over this failure that happened at an ethylene plant in 2002. So just describing the process overall is that it was an olefins ethane cracker with a flow stream of demethanizer first and a back-end acetylene converter. So as you can see on the screen, this is the cold flare drum where the contents are vaporized and superheated using a closed loop propanol system where heat is applied to the system using 70 pounds of steam that is operating at around 270 degrees Fahrenheit, and heat is applied to the cold flare drum with the use of this cold flare vaporizer and this cold flare superheater that's in place. Now, the failure scenario starts when the process plant, it produces an off-spec product at the ethylene converter, which leads to flaring of the ethylene product via the cold flare drum. So through a sequence of events, what happens is the cold flare overhead line that you can see on the previous slide, I'll just go back to it right here, that is made of carbon steel and that has a minimum design metal temperature of minus 10 degrees Fahrenheit. And we'll get back to the failure that happened. So what happens is the temperature, because the cold flare superheater in the cold flare superheater and the cold flare vaporizer, they have not been maintained properly and they have not been operated well over a period of time. It has caused fouling of the and it does not meet the heating capacity requirements that are required for the cold flare drum. So as a result of that, what happens is the temperature of the cold flare drum in the overhead line drops below your minimum design metal temperature. And what happens is brittle fracture happens on the carbon steel piping because it has gone below the MDMT. And as you can see, there is a fire scenario that happened because the ethylene product auto-ignited, and that's how the fire happened. And you can see a section of that carbon steel piping that just fractured off as a result of that brittle failure. Now going through some of the chemical processes that can cause failures on your equipment. The first scenario is high chloride content in cooling water and steam generation systems, where chlorides can condense and they can cause chloride stress corrosion cracking in equipment that is made of 300 series stainless steels. And you can also have ammonium chloride concentrations in overhead crude and hydroprocessing units, which are basically caused because you have ammonia streams that are added to overhead lines to increase the pH that is caused by the presence of hydrochloric acid in crude streams that are present. And what happens is, in the presence of H2S, the materials of the crude, when it reacts with the ammonia, it precipitates into ammonium chloride, and you can have some under-deposit corrosion and some local pitting as a result of this. The next scenario is your low pH levels. So the first scenario I'd like to cover is sulfuric acid addition to the alkylation units. So in an alkylation unit, you have sulfuric acid, which acts as a catalyst to convert low molecular weight alkenes to alkylate, which is a high octane gasoline component, which is typically used as blending fuels in gasoline to produce higher octane fuels that may be present. So what you can have is sulfuric acid corrosion, which is characterized by low shallow pitch on carbon steel and low alloy steels. And the image on the bottom left corner gives a pretty good example of where sulfuric acid corrosion has created grooves on this metal right here, as I can show you on the image. That is another type of failure that can happen. Now, in boiler feed water systems and condensate systems, you might have dissolved carbon dioxide, which can turn into carbonic acid and can cause CO2 corrosion, which is characterized by local thinning and pitting on carbon steels. As you can see right here, the image on the right is a pretty good picture of some pits and some thinning that happened on steels that were exposed to this kind of corrosion. Now, let's look at some ways that you can monitor, prevent, and detect some of these damage mechanisms that may be present. The first thing would be to monitor your equipment. And the first thing to do is identify process conditions that may be causing these damages onto your equipment. The next step to do would be to define limits that may be governed by the design of your equipment, your metallurgy, your wall thickness. A good example is your maximum allowable working pressure, or your MAWP, which may be defined by your material strength, which is a characteristic of your metallurgy, your wall thickness, your weld strength, can affect what operating limits that you might have on your equipment as far as pressure is concerned. The next thing is to implement or install necessary systems and processes that are capable of tracking these variables. And by that I mean installing instrumentation that is capable of monitoring all these process variables over time, and see if you are operating above or below your limits that you have set for the equipment. The next thing is to document and evaluate results, and to ensure that these results are evaluated by subject matter experts who are experts in the field, and they know what kind of damage mechanisms to expect and what remedies that you can have to prevent them. The next step is prevention. Wherever you might have process variables that are high risk, you might introduce automated process control that may be needed for a more immediate response, so that it does not go above your set limits. A good example for this is if you have a knockout pot that has, for example, a volatile fluid like H2S inside it. Whenever you have an overfill scenario, you might want to have level control that just shuts down a pump or shuts down a motor valve that provides input onto there. Where you don't have enough time for the operator to respond to that scenario, that's where you would use automated process controls. An emergency shutdown system is also a pretty good example of how automated process control can reduce risks to your fixed equipment. The next thing is to provide additional relief protection and to prevent overpressure and vacuum scenarios. A good example is the one that we saw about the vacuum scenario, where the equipment did not have adequate vacuum protection to prevent it from collapsing towards the inside. The next step is to introduce standard operating procedures that can be written, and the operator can respond to the changing process variables. A good example for this is, suppose you have a large storage tank that is filling up really quickly. So you might have an operator go up and shut down a pump or close a valve that is going in because you have time to respond before it reaches your process variable limits in that case. And wherever you cannot follow any of these steps that I have listed above, you might even, as a last resort, redesign or modify the equipment that is in place to meet these criteria. Again, prevention and monitoring is not enough to foresee what kind of new damages that you can introduce into the system. Wherever there are process changes that can affect the integrity of your equipment, or from past inspections you have identified process damage, you must try and do more inspections, and I think non-destructive examination methods are a good example or a good way to go forward while doing that. Now, I'd like to briefly describe what is an inspection plan and how inspection plans are pretty relevant. The first thing is an inspection plan should be for each piece of equipment that is available at your, that is operating at your facility. And the contents of an inspection plan should be the frequency of your inspection, how frequently you're going to do inspections, which is defined by codes and standards. Your methods of inspection, that is again defined from your previous experience, what kind of damage you are predicting, and what type of NDE method you can use, and we'll cover some of the NDE methods coming in the next slide. Another step is finding the location and coverage of the inspection. A good example is for cracking. I can think that whenever you have cracks in your equipment, you can see it is very common that it is in your heat affected zones that are close to your wells. So you might have a description in the inspection plan that says inspect all the heat affected zones on all the wells that are available inside this equipment. You might also have some internal components that have some corrosion or have some tendency to corrode when you introduce some process changes. So all that should be part of the inspection plan. The next step is to identify corrective actions after you document all these results. That would be to repair if you have any cracks, or wherever you see damage, what kind of repair should be made. That should be part of the inspection plan. Another thing is, if you see any new forms of damage that you haven't seen in your previous 2 or 3 or 5 or 6 inspections, it might be worth, it is standard to put those new results as part of the inspection plan. Suppose you found cracks that are not close to the well, you found them on the shell portion, then you might say that we have to do some specialized crack inspections when the next inspection is due, or you might, even in the same inspection, you might say that we have to do a cracking inspection of the entire shell because we found 1 or 2 cracks on the shell portion. So that is how you have to update the inspection plan based upon what findings you have. So some of the non-destructive examination techniques include visual examination, where you can find deformations, like we discussed about plastic deformation in the overpressure scenario, and some visible cracks that might come from chloride stress corrosion cracking that we discussed earlier, and any other visual deformities that you might have, especially in like internal components inside reactors and vessels. A more advanced technique is ultrasonic thickness readings, which will help you to re-evaluate your equipment based upon your thickness, about whether you should degrade your equipment or whether it's good for whatever remaining life that you have. Another thing is taking thickness readings can give you corrosion rates, and corrosion rates will determine when you want to do your next inspection and what frequency of inspection that you should have based upon what value you get for your corrosion rates. And if you are finding more defects on your equipment, you might even consider some advanced ultrasonics or radiographic examination to locate subsurface cracks and internal cracks that may be present, and even identify some well deficiencies that may be present. Now I'll go back to some of the scenarios that we covered and what we could have done from prevention, monitoring, and detection methods from all those case scenarios. For the overpressure and vacuum scenarios, it's important to ensure that all your pressure indicators are working and you have pressure indicators on all your equipment to monitor them. The next thing is to, like I said, to confirm that you have adequate relief protection installed and that it is sized properly and it is set properly. One thing that we commonly find is whenever equipment is derated or whenever you have lowered the MAWP of the vessel, sometimes the relief protection is not updated in many facilities. So it's important to ensure that you do that. The next step is to ensure that visual inspections are performed and they are performed at an appropriate interval. So this can help you find if there are any deformations or if there is any damage to like internal components in your equipment. The next step is to introduce automated process engineering controls to prevent overpressure or any other process scenario from happening. The last one, like I described, is the use of standard operating procedures, like I described in the example with the levels of those tanks and that H2S knockout pot. The next scenario is operating within the corrosion under insulation range. It's important to screen the equipment based upon temperature that you're operating at and your metallurgy, whether it's carbon steel or stainless steel, within that temperature range that I described in the previous slides. The next step is to periodically remove insulation and perform visual inspection so that you ensure that there are no leaks on the system that are caused due to CUI. But as I said, this might be a more expensive process, and you might have to build scaffoldings and access requirements where piping and equipment cannot be easily accessed. So in that case, you might have some advanced CUI screening techniques. One thing I can think of is real-time radiography is a pretty good technique where you can see the internal components of your pipe, whether they have corrosion on them or what is the current status of all your equipment that is inside the insulation. For equipment that is operating below your MDMT, what you can do is you can perform a hazard evaluation to identify equipment that have potential auto refrigeration and brittle fracture scenarios. And you can do some inspections for cracks that you might find when the equipment has operated below your MDMT, because cracks become the initiator for causing brittle fracture due to MDMT in many of these equipments. When you have chloride stress corrosion cracking, you might have some specialized inspection techniques based upon the metallurgy. You might use dipenetrant or magnetic particle inspections, magnetic particle techniques to identify cracks that are on the surface. For volumetric cracks, you might have to use advanced ultrasonics to find or flaw detection methods like shear wave to find out what kind of cracks are present inside the volume of the material. And a more expensive remediation would be to upgrading to higher resistance alloys that are nickel based. And by nickel based, I mean something that has nickel content between 35 and 45%. If you have nickel alloys that are between 8 and 12%, they are still susceptible to chloride stress corrosion cracking. Now going to lower pH levels. Corrosion, you can minimize sulfuric acid corrosion by using better alloys, like I said, and Hastelloy C276 is really resistant towards sulfuric acid corrosion. For carbon dioxide corrosion, what you can do is the use of corrosion inhibitors or the use of 300 series stainless steels can help mitigate and prevent CO2 corrosion. Now, what are some of the elements that you should incorporate in your FEMI program? The first step is to establish integrity operating windows. This is to ensure that you have, the first step would be to ensure that you have sufficient instrumentation and other processes that exist to ensure that the system is monitored. This would be your pressure transmitters, your temperature transmitters, and your analytical elements that can provide sufficient information about what level that you're operating at. And whenever these process variables go above or below your IOWs, it is important for the system to alert and to take necessary steps like for example, you have a fired heater that is operating above your integrity operating window. Suppose the fired heater had a life of about 100,000 hours when it was operating at 900 or 950 degrees Fahrenheit, and you operated it at around 1050 degrees Fahrenheit. So your consequence would be your reduced life. So whenever you are operating above or below your integrity operating window, it is necessary to do some follow-up action. You might do some inspection techniques to find out whether there is any damage that has been caused due to you operating that equipment above the IOW. The next step would be to evaluate and validate your relief protection. This is to, again, ensure that your relief protection is well maintained, your relief devices are tested on a specified frequency, and that there is a process in place to ensure that relief devices are set again, after you maintain and test your equipment, that it is again set to the proper MAWP or proper set pressure that you want for that equipment. Doing a corrosion or damage mechanism study, again, I'd like to stress the fact that a damage mechanism study should be done by experienced subject matter experts. That can be your experienced reliability engineers, your inspector who has been working at the unit for multiple number of years, your process engineers, and your corrosion or your material specialist who has knowledge about the different corrosion mechanisms. Your next step would be to establish and update your equipment inspection plan based upon your IOWs and all the other steps that I described. Whenever appropriate, you should increase the frequency. Whenever you find damage, you should increase the frequency of your inspection so that you get to know and you can repair all those damages that you find. And the next step would be to perform non-destructive examination techniques like I previously described, where there is potential for damage and where previous damage has already been observed. This could be, like I said, with the cracking example, like I said, on heat affected zones, or wherever you see some chloride concentrations, or on nozzles, wherever you have, in heat exchangers, wherever you have heavy fluid coming in, you would ideally inspect the opposite section where fluid impinges into your heat exchanger. So those might be like specific areas that you might inspect based upon your experience. And then the type of NDE, like I said, with respect to the cracking example, the type of NDE should be based on the type of damage that you have expected. Now, what I'd like to do is that concludes the informational part of my webinar, but one thing I'd like to ask the audience to do is to ask questions whether process conditions are being properly considered at your facility that you work at. Many facilities have addressed the basic requirements of the API codes for inspecting their equipment, but I think my end goal as a result of this webinar is to provide you with the tools to improve the safety of your facility and reduce the overall risk by taking steps and having discussions within your facility to incorporate these process changes into your FEMI program. So some of the questions that I want the audience to take back is what I've listed in the next two slides, and I'll go over them one by one. Does your facility have a well-documented relief system design basis? And if so, is it up to date? If you have performed the revalidation, how recently have you performed that? and whether have you taken these process conditions into effect while revalidating your release systems basis. Have you established integrity operating windows at your facility, and if so, have you provided training to your operations personnel and updated your alarm settings and operating procedures based upon these adjusted IOWs? Has a corrosion study been performed to determine whether there are certain types of damage mechanisms that might be existing in your facility? Have you consulted this with a corrosion specialist or an experienced inspection person who knows about the specific damage mechanisms that are present at your facility? Do all your equipment have equipment inspection plans, and whether they have been defined or modified based upon whatever corrosion study that you've made? And lastly, is there a robust enough MOC process that can ensure that all the changes that you're making, all the process condition changes that you're making, that could affect your fixed equipment and your personnel working at your facility? So I think with that, I'll come to the end of my presentation, and then I'll be ready to take some questions.
Okay, thank you, Vipin. If anyone has any questions, they can please send them to host in the chat box, and I'll ask them of Vipin. So we have a few. What are some of the NDE, non-destructive examination techniques used for detecting cracks?
Well, something that I can think of are, it's really dependent on the metallurgy and where the cracks are. So if you have like surface cracks, and if you have them on like carbon steel vessels that are ferromagnetic, I would say that magnetic particle inspection is a pretty good inspection technique for them. And if you have cracks on stainless steel equipment, dye penetrant techniques are pretty good as far as surface cracks are concerned. But if you have any volumetric cracks, then I think advanced ultrasonic, something like a shear wave, is a pretty good technique to find flaws, and you can even find the size of the flaws by using advanced ultrasonic techniques.
Okay, thank you. Is the IOW established during FEED, feed?
You can. If you have a similar facility, then you can. Otherwise, I think API 584, it's a relatively new document that has come out. So I think going through API 584 can give you some guidelines about establishing IOWs. That is, I think mostly it's based on whatever experience that you can have. But I think if you have similar facilities, you can have, you can duplicate IOWs from different experiences that you have.
Okay, thank you. Is there a standard which describes how to conduct a corrosion study?
Corrosion study. I can't think of anything right now, but I think API might be coming with something very soon. As far as if you want to know about damage mechanisms, about specific damage mechanisms, then I think API 571 is a really good guide, and it's very, very comprehensive as far as defining corrosion damage mechanisms. But I think the methodology that you're talking about, I think some companies might have corporate procedures, but as far as an industry standard goes, I don't think there is any as far as establishing a corrosion control. If you're asking about establishing a corrosion control document.
Okay, thank you. Can a process fluid having a high pH also cause some form of damage to fixed equipment?
Yes, it surely can. Because of the time limit of my webinar, I did not cover caustic stress corrosion cracking. That typically happens to carbon steel equipment and piping that have not been stress relieved. Whenever you have welding done on them on welds like elbows and T's, you might have, if you have not done any stress relieving processes, and you have caustic fluids that are greater than 50 ppm, between 10 and 50 ppm, and operating in between, let's say, I think if I remember correctly, between 120 and 180 degrees Fahrenheit, you might have some caustic stress corrosion cracking.
Okay, thank you. What type of damage can be caused due to high flow rates, and how can you prevent them?
One that I can think of off the top of my head is erosion corrosion that you can have. which is a mixture of corrosion and erosion due to the high velocities that are inside piping and pressure equipment. One remedy that I can suggest is, if possible, increasing the size of your pipe to reduce the flow velocities, whatever is there inside, and also to use better metallurgies. Like I said, for sulfuric acid corrosion, you might have to use an alloy like C276, which has excellent resistance to sulfuric acid corrosion.
Okay, thank you. If anyone still has a question that they haven't asked and they would like to get a response, you can send it on to me at producer@aiche.org, and I will send it on to Vipin. So now, on behalf of the American Institute of Chemical Engineers and everyone who attended today, I'd like to thank Vipin Vijayakumaran for this informative presentation. Thanks also to our participants for your cooperation and thoughtful questions. Please visit aiche.org to replay this session or to view and sign up for our many others. Goodbye, and we hope to see you again in a webinar soon.
Thank you. Thank you, Pamela. Thank you to the audience.
Thank you.